Hello, welcome everyone to the next Gen 4 International Forum webinar. Today's presentation is on the design, safety features, and progress of the HTR-PM. Our presenter today is Professor Dong, joining us from China. Before we get started, I just want to take a few minutes to do a little bit of housekeeping. There's a Q&A pod for you to type in questions that you may have for the presenter to answer. We will take those questions following the webinar presentation. So go ahead and just type those into the Q&A pod. We will read those questions and field as many as we have time for at the end. In the second pod below the Q&A pod, it's labeled Files 2. There is a PDF copy of today's slide deck. If you click that, that will download that PDF right to your laptop or your workstation. And finally, in the notes pod is a link to an online survey where you can provide feedback and answer some questions about the GIF webinars and today's presentation in particular. We do appreciate that feedback and take your comments seriously. We're very anxious to hear about ways that we can improve and ideas for future webinars. So take a few minutes, please, after today's presentation to complete that survey. So without any further ado, I will get started. Dr. Patricia Pavier is the Director of the Materials and Chemical Technologies Office in DOE, Office of Nuclear Energy. She's also the Chair of the GIF Education and Training Task Force. Patricia?
Yes, thank you so much, Bertha, for the introduction, and I'm very happy today to have Dr. Dong with us. He's a professor in nuclear engineering at the Tsinghua University in Beijing, China, where he earned his PhD degree in nuclear reactor engineering and safety. Since 1997, he has worked to develop advanced nuclear reactors at the Institute of Nuclear and New Energy Technology at the Tsinghua University. He has served as the head of the Division of Reactor Thermal Hydraulic Calculation and head of the Division of Reactor Physics, Thermal Hydraulics, and System Simulation. In 2006, he was responsible of the Division of General Design of High-Temperature Gas-Cooled Reactor. Currently, he is the Deputy Director and Deputy Chief Engineer of INET in charge of HTGR projects. In addition, he has also been appointed by the National Energy Administration to be the Deputy Technical Director of the HGTR Nuclear Power Plant project, which is one of the national science and technology major projects. He is actively involved in planning the system arrangement of VHTR as a member of the System Steering Committee in the frame of GIF. So thank you again, Professor Dong, for volunteering to give this webinar. And without any delay, I give you the floor. Thank you again.
Hello, everyone. It's my pleasure to give a presentation on China High-Temperature Gas-Cooled Reactor Demonstration Power Plant Project, HTR-PM project. My name is Yujie Dong from INET Tsinghua University, Beijing, China. Today, I will give a comprehensive introduction to HTR-PM project. I hope that a participant can learn the complete and the rough process of HTR-PM development. This presentation includes the design of HTR-PM, safety of HTR-PM, pre-construction preparation, demonstration test, procurement of components, construction, fuel, and follow-up project. In China, the R&D program for the high-temperature gas-cooled reactor in INET, Tsinghua University, began in the mid-1970s. HTR-PM has been developed on the basis of HTR-10, a 10 megawatt high-temperature gas-cooled test reactor. In 1986, the R&D work on design and component technologies was started under the support of a National High Technology Program. In 1992, construction of HTR-10 was approved. In June 1995, the reactor construction was started. In December 2000, first criticality was achieved, and in January 2003, full power operation was achieved. The top right figure shows the primary circuit of HTR-10. It is designed according to modular concept. On the left, it is the reactor body, and on the right, they are steam generator and blower. The bottom right picture shows the appearance of HTR-10. HTR-PM is an acronym of High Temperature Gas-Cooled Reactor Pebble-bed Module. It is aimed to extend the nuclear energy application beyond the grid, including cogeneration, high-temperature heat utilization, and hydrogen production. The prospects of HTR-PM development in China consists of three aspects. Firstly, to be a highly efficient nuclear power technology as a supplement of PWR technology. Secondly, to be a major technology in nuclear process heat. And thirdly, to contribute globally through innovation in advanced nuclear technologies. The technical goals of HTR-PM comprise 4 points. Firstly, to keep inherent safety. This is the most important technical goal. Secondly, to achieve economic competitiveness comparing with other nuclear power plants. Good economics is the foundation on which the technology can be promoted. Thirdly, to realize standardized design. That means future power plants can be built entirely on the standardized module. Finally, to use proven technology as much as possible in order to reduce technical risks. How to use proven technology? Firstly, we use the technology demonstrated on HTR-10. Secondly, we try to learn useful global experience. For example, using German HTR module and the United States HGTR as reference, learning other international achievement and experience. Thirdly, we choose steam turbine in the power conversion system as the first step, not a gas turbine. Finally, we purchased some key components globally. Regarding the general design of HTR-PM, we made several comparisons when we conducted standard design. Before 2006, we studied a annular core with power of 458 megawatt thermal. We compared the annular cores with different central graphite columns, dynamic and fixed columns. We compared the different steam cycles, reheating and non-reheating cycle. After these comparisons, we determined the final technical solution in 2006. Two cylindrical core of 250 megawatt coupled to one steam turbine. The features of final design can be summarized as follows. Steam turbine cycle is used as a power conversion unit. Two NSSS are coupled to one steam turbine. No reheating in secondary circuit is chosen. Simple cylindrical core is chosen. fueling mode is multipass charge continually. This figure presents the overview of HTR-PM. The HTR-PM demonstration power plant consists of reactor building, auxiliary building, spent fuel building, electrical building, and steam turbine building. There are two entry phase modules in the reactor building. They are connected to one steam turbine generator. The spent fuel element will be stored in the spent fuel building. The left figure illustrates the composition of one entry phase module. For each module, there are one reactor, one steam generator, and one blower. They are installed into two separate vessels. The vessels are assembled in a stacked side-by-side arrangement and connected by the connecting vessel. The reactor core comprises of lots of pebble fuel elements. Around the fuel zone, there are graphite blocks acting as reflectors. The reactivity control system are arranged on the top of a reactor pressure vessel, including control rod, driving mechanism, and a small absorber sphere system. The fuel elements are charged at the top of vessel and discharged at the bottom. The blower is arranged above the steam generator. The right table lists the main parameter of HTR-PM demonstration power plant. Total electrical power 211 megawatt. Each reactor module, the thermal power is 250 megawatt. There are totally two entry phase modules in the demonstration power plant. The diameter of the reactor core is 3 meters, and the height of core is 11 meters. The primary helium pressure is 7 megapascal. Core outlet and inlet temperature are 750 and 250 degrees Celsius. Fuel enrichment is 8.5%, and the steam conditions are 13 megapascal and 567 degrees. Next, I would like to give a brief introduction to main components. Blower is the heart component of HTR-PM. The main design parameters are as follows. The pressure rise 200 kilopascal, temperature of helium 250 degrees, rotation speed 4,000, and the electrical power is about 4,500 kilowatt. Next, I would like to give a brief introduction to, in the design of blower, an internal vertical layout was selected. The blower is driven by high-speed, frequency-control electrical motor. A single-stage centrifugal impeller is installed. Especially, active magnetic bearing is assembled. We selected active magnetic bearing for the blower because we wanted to place the blower into the primary press boundary. This configuration can ensure the helium sealing and prevent lubricant leakage into the primary circuit. Steam generator is another important component. It generates high pressure and high temperature steam. The heat transfer tubes are boundary of primary system. The steam generator is a vertical counterflow one-through type. Feed water flow in from the bottom of steam generator pressure vessel, and steam flows out from the top of vessel. We selected a medium-sized, multiple-layer helical tube assemblies in order that in-service inspection is feasible and flow distribution is testable. A full-scale assembly can be tested and verified in the 10 megawatt thermal helium engineering test facility. The main design parameter of the blower as follows. The total thermal power is 253 megawatt. There are 19 assemblies in each steam generator. Every assembly has a heat transfer capability of 13 megawatt. For each assembly, there are 35 heat transfer tubes. The total number of tubes is 665. There are two categories of independent systems for reactivity control purpose: control rods and small absorber spheres. They are all located inside the reflex. The neutron absorb is boron carbide. There are totally 30 graphite blocks in the circumferential side reflex. Control rods act as primary reactivity control system. There are 24 motor-driven rods in each module. The reactor can be shut down, started up, and operated only through control rod movement. Small absorber sphere system act as reserved reactivity control systems. There are 6 sets of SAS systems. The small spheres will fall into the hose by gravity and will be returned through pneumatical conveyance. As you know, for our HTR-PM, the fuel element will be inserted into reactor core every day. Therefore, the fuel handling system is also a very important system. Every day, fresh fuel elements are charged, spent fuel element will be discharged. Meanwhile, the burn-up of each used fuel element will be measured. If the burn-up reaches designed value, it will be transferred to the spent fuel storage tank. Otherwise, the fuel element will be sent back to the reactor core. In addition, the broken element will be filtered out by this system. Next part, I will introduce the safety of HTR-PM. The worldwide nuclear community has made great efforts to find a solution for the problem of nuclear energy safety. Of this, the modular high-temperature gas-cooled reactor is one of the most innovative and challenging technologies. Any nuclear energy system must fulfill the following nuclear safety functions. First one is the control of reactivity. The second one is the removal of heat from the reactor and from the used fuel storage. The third one is confinement of radioactive materials, shielding against radiation and control of planned radioactive release, as well as limitation of accidental radioactive releases. HTR-PM can fulfill above safety requirements perfectly. However, HTR-PM implements these safety functions differently compared with other types of reactors. Control of reactivity is similar to that of PWR reactors, but HTR-PM possesses its own characteristics. The related features are as follows. Firstly, there is only small reserved reactivity due to continuous fuel loading. Nearly no insertion of control rods in normal conditions. Only reserved reactivity for power regulation is balanced by control. Secondly, helium is transparent to neutrons. The variation of helium inventory will not cause reactivity change. Thirdly, depending on full-scale negative temperature feedback, large temperature margin, the reactor can be shut down automatically. Any insertion of positive reactivity related to an accident can be compensated by negative temperature feedback. For example, water ingress accident. Passive removal of deck heat is unique and also the most important feature of HTR-PM. It is inherent safety. That is, no need of power supply, no need of working fluid. During the local accident, the deck heat will be radiated to the cooling panel around the pressure vessel. The left curve shows the change of maximum fuel temperature during local accident with the elapsed time. The peak value of fuel temperature will appear after 20 hours. After this peak value, the fuel temperature will go down slowly. The right figure shows the maximum temperature distribution at the time of peak fuel temperature. Maximum fuel temperature is always lower than the limit temperature of materials during the accident. Even if the cooling panel fails, the maximum fuel temperature is still lower than the limit value, although the reactor pressure vessel will withstand higher temperature. The deck heat will be transferred to environment through concrete wall. This figure shows the structure of a fuel element. In each fuel element, there are 10,000 coated particles. For each tracer-coated particle, there are several coated layers outside the uranium kernel, including loose buffer layer, dense pyrolytic carbon layer, and silicon carbide layer. For HTR-PM, the key barriers for confinement of radioactive materials are coating layers of fuel particles, especially the silicon carbide layer. In each module, there are about 400,000 fuel elements. That is 4 billions of coated particles. The failure rate in manufacture and operation is very low, lower than 10 to the minus 4. There is no likelihood of massive failure in accident. Silicon carbide layer can resist intrusion of external water and air. In addition to the coated layers, there are also complementary barriers, including reactor vessel, vented lower pressure confinement. This drawing illustrates the relationship between normal and accidental temperatures and the tolerant temperature of a tracer particle. During normal operation, the average temperature of fuel element is about 600 degrees. The maximum temperature is only 900 degrees. But the designed limit temperature of a fuel particle is 1620 degrees. And the temperature of decomposition of silicon carbide is above 2100 degrees centigrade. Therefore, there is a large temperature margin for the fuel particles. Next part is pre-construction preparation. From 2001, on the basis of success of HTR-10, we started HTR-PM conceptual design. In 2006, this project was listed by central government as one of key projects in China. In 2008, the implementation planning was approved, including target, schedule, funding, R&D program. The target of the project is to complete the 200 megawatt HTR-PM demonstration plant and for providing sound foundation for the further development of Generation 4 nuclear system. Within this project, there are 3 close and key partners, INET, Change, and Shandong Shidao-Bei Nuclear Power Company. INET is responsible for technical research and development, general design, and design of main systems and components. Change is the EPC main contractor of Nuclear Island and its BOP. It was jointly invested by China Nuclear Engineering Group Corporation and Tsinghua Holdings in 2003. China Guangdong Nuclear Power Corporation became one shareholder later. Shandong Shidao-Bei Nuclear Power Company is HTR-PM owner for construction and operation. It was jointly invested by China Huanan Group, China Nuclear Engineering Group Corporation, and Tsinghua Holdings. The HTR-PM site is situated at Shidao-Bei, Rongcheng City, Weihai, Shandong Province. In 2008, the preparation on site was started. The primary task was the excavation of a nuclear island building. In 2007, the feasibility study of HTR-PM project was finished. Feasibility study report was checked by a consultant in 2008. Environmental impact report at the feasibility study stage, site safety analysis report were approved by National Nuclear Safety Administration in 2008. In 2008, basic design of HTR-PM demonstration plant was finished. Basic design documentation and drawings were reviewed in 2009 by a consultant. Before review of the preliminary safety analysis report, design criteria of HTR-PM had been reviewed by NSA. The technical document titled Important Criteria for HTR-PM Safety Reviews were finished by NSA in 2006. In 2008, the PSAR was submitted to NSA for review. Following above-mentioned documents, major nuclear safety reviews at the construction permit license stage were finished. The PSAR was approved in 2009. In order to carry out demonstration tests, a specialized laboratory was built and was ready for testing in 2010. In order to simulate the high temperature, high pressure helium circumstance, a large-scale helium loop was built. The test power is 10 megawatt, temperature is 750 degrees, the pressure is 7 megapascal. The coolant is helium. There are same as conditions of reactors. In this laboratory, a series of full-scale demonstration tests were arranged. One assembly of the steam generator, a full-scale prototype helium circuit, a full-scale fuel handling system, a full-scale prototype control rod driving mechanism system, a full-scale small absorber sphere system, a full-scope helium purification system, a prototype reactor protection system and control room were planned to be tested here under cold and hot conditions in helium atmosphere. As of July 2017, all demonstration tests had been finished, including control rod driving mechanism, small absorber sphere system, control room, helium circulate, spent fuel canister, fuel handling system, steam generator. The components of HTR-PM were manufactured based on the prototypical components which have been demonstrated. We carefully developed the helium blower step by step. Totally, we manufactured 4 prototypes. Prototype number 1 is a full-scale motor with oil lubrication bearing. Number 2 is a motor with domestic magnetic bearing. Number 3 is a full-scale helium circulate with domestic bearing. Number 4 is a full-scale motor with the magnetic bearing of the final product, testing the catch-down capability. In 2014, in Shanghai Blower Company, we finished a 100-hour hot test and a 500-hour hot test in nitrogen atmosphere. In 2015, in INET, we finished the 50 hours test in helium atmosphere, and in 2016, we finished the 50 life cycle test in helium atmosphere. For every cycle, from cold to hot, the blower experienced 10 transients. The test comprised totally 500 transients, and they took 6 months. In 2016, we finished the extreme condition test in helium atmosphere. As of October 2016, the full-scale engineering test of fuel handling system was finished. In 7 megapascal, the hot helium atmosphere, the fuel handling system experienced 500 hours automatic operation. The test demonstrated various process of fuel handling system. In July 2017, the hot test of an assembly was finished. The test power is 10 megawatt. Helium conditions are 750 degree, 7 megapascal. The steam conditions are 570 degree, 14 megapascal. This test demonstrated the thermohydraulic performance of steam generator assembly. This is also the last demonstration test. Next part is a component. Because main components of HTR-PM are first-of-a-kind equipment, they need a much longer lead time. Therefore, by the end of 2008, main components were ordered, such as reactor pressure vessel, steam generator, blowers. Due to China's industrial capability, we have overcome greater difficulties during the manufacturing first-of-a-kind components. At present, 2 reactor pressure vessels have been installed. 2 sets of metallic reactor internals have been installed. The full scope simulator has been put into operation. The distributed control system has been installed. The reactor protection system has been installed. First batch of control rod driving mechanisms have been delivered and are being installed. First batch of small absorber sphere system have been delivered and are being installed. 2 helium circulator will be delivered soon. Components of fuel handling system are being installed. The steam generator is delayed. The steam generator is the most difficult piece of equipment to manufacture in many of its aspects, including materials, rolling and bending the heat transfer tubes, assembling the heat transfer unit, final assembling, welding, special tooling and workshops, and so on. Currently, all assemblies and tool vessels have been provided. They are in final assembling in factory. This picture shows the final state of one reactor pressure vessel before delivery. The reactor pressure vessel is the largest component in this project. It's about 700 tons in weight, 25 meters in height and of main body. Its outer diameter is about 6 meters. After overcoming some initial difficulties in forging manufacturing, the manufacturing of reactor pressure vessel was proceeding smoothly. The picture on this slide shows the full-scale simulator and main control room. The component of main control room was supplied by Shanghai Automation Instrumentation Corporation. Main component suppliers are as follows. Shanghai Electric provided the reactor pressure vessel, metallic reactor internals, control rod driving mechanism, SAS, steam turbine, helium circulate. Harbin Electric is responsible for manufacture of steam generator and electricity generator. Toyo Tanso of Japan provided graphite blocks. China General Nuclear Power Corporation supplied DCS and full scope simulator. Other components have been supplied by companies inside and outside China. For example, we purchased some valves from German and French companies. Next part is construction. Some milestones of construction are listed here. On 9th of December 2012, we started construction of HTR-PM, which is the first concrete powering date. HTR-PM was the first new project which had been approved of construction after Fukushima accident. Actually, this project was approved by central government on 1st of March 2011. That was 10 days before East Japan earthquake. We planned to start the construction around the end of March 2011 due to occurrence of Fukushima accident. China carried out a complete safety check of nuclear facilities, including operating nuclear power plants, nuclear power plants under construction, and the nuclear power plants which were ready to be constructed. The post-Fukushima safety inspection was finished in 2011 and approved by government in 2012. In June 2015, construction of a reactor building was finished. In December 2015, the full scope simulator was delivered. In March 2016, first reactor pressure vessel was installed, and in September 2016, another RPV was installed. In October 2016, inverse transmission power was achieved. And in June 2017, the ceramic internals of first module were installed. In September 2017, graphite pebbles were loaded into the core of first module. In last December, the head of first reactor pressure vessel was hosted in place. After the construction permit license was issued by the NNSA of China and all government approval procedures were complete, the first concrete of HTR-PM demonstration power plant was poured. This picture shows the occasion of FCD. As you see, the foundation was covered by snow. It was very cold that day, but we were really excited because we could start construction of HTR-PM finally. The altitude of foundation is minus 18 meters. We decided the bottom plate into multiple layers and multiple sections in order to assure the quality of concrete pouring. This picture shows the spectacle of hoisting the reactor press vessel into the reactor building. A large crane with a capacity of 3,000 tons was used for lifting the reactor press vessel. Top left picture shows the scene of hoisting the biggest core internal core barrel. The top right picture shows the head of reactor pressure vessel being hosted last December. And the bottom picture shows the current overview of HTR-PM demonstration power plant. Qualified fuel elements are crucial to success of this project. Firstly, INET established one demo production facility. Its capacity is 100,000 fuel elements per year. We produced a batch of fuel elements with the facility and sampled 5 elements for irradiation test. In October 2010, started the irradiation test of fuel element in Beijing, the Netherlands. From 2012 to 2014, this irradiation test lasted 350 equivalent full power days. This picture shows the demo production facility, the sampled element, the capsule used in irradiation test, and the result of irradiation test. The results are very good, no any particle failure. Up to now, the heating test of irradiated fuel element have been finished in Karlsruhe, Germany. The test results are also very good. On the basis of demo production facility, a commercial fuel plant was established in Bottle Fuel Plant, North China. Its capacity is 300,000 fuel elements per year. In March 2013, construction was started, and in March 2016, the plant installation and commission were finished. In August 2016, the production was started. Up to December 2017, more than 300,000 fuel pebbles had been produced. This fuel plant can supply enough fuel elements for HTR-PM demonstration power plant. This picture shows the internal and external view of a fuel production plant. After completion of HTR-PM demonstration power plant, how to deploy HTR-PM? There are two options. One is to duplicate HTR-PM demonstration power plant. Another option is HTR-PM 600. Basic ideas of HTR-PM 600 can be summarized as follows. 6 reactor modules are connected to one steam turbine. The electrical power is 650 megawatt. Compared with HTR-PM demonstration power plant, HTR-PM 600 possesses the same safety features, use the same major components, and operate within same parameters. The economics of HTR-PM 600 will be better. We have finished the preliminary design of HTR-PM 600. The cylindrical reactor building occupies the same site footprint and the same volume comparing with the same size pressurized water reactors. In China, there are 3 plant owners for HTR-PM. One is China Huaneng Corporation, another one is China Nuclear Engineering Corporation, and China General Nuclear Power Corporation. Feasibility study of several sites have been finished and reviewed by consultants, including Sanmen, Zhejiang Province, Ruijin, Jiangxi Province, Xiapu, Fujian Province, Wan'an, Fujian Province, Bai'an, Guangdong Province. At the Sanmen site, we will try to replace a planned coal-fired plant with HTR-PM 600. In summary, HTR-PM is a Pebble-bed modular high-temperature gas-cooled reactor. It possesses inherent safety. A simple cylindrical core is chosen. A steam cycle is used for electricity generation. All key components and technologies have been tested and verified. Most components have been delivered on schedule. The construction of the plant is smoothly going. A specialized fuel factory has been put into operation successfully. Next step, 6-module unit, that's a commercial 600 megawatt electricity unit, will be deployed as a supplement to PWR. For example, replacing coal-fired power plant, cogeneration of steam and electricity. Thank you all very much for your attention. Especially, I would like to thank Patricia and Berta for their great preparation for this webinar. And I would like to thank Professor Sun Jun for his help. Thank you.
Thank you, Professor.
And
please be my guest. And if you have questions for Professor Dong, There are some I see in the Q&A pod, but go ahead and type questions that you may have remaining in there, and we will address those. While those questions are coming in, the upcoming webinars, the GIF webinars, in February, we'll have a presentation on the Gen 4 reactors, materials, and their challenges by Dr. Malloy with the Los Alamos National Laboratory in the USA. And in March, we have a presentation planned on SCK CEN's R&D on MYRRAH by Professor Abderham from Belgium. And in April, the presentation on Russia BN 600 and BN 800 by Dr. Ashurko from Russia.
Yeah, thank you again, Professor Dong, for this excellent presentation. As the chair of the GIF Education and Training Task Force, I take also this opportunity to announce an international training course which is supported by the GIF Task Force. It's on Generation 4 Nuclear Reactor System for the Future. It will be in Saclay in Paris. It's 20 kilometers from Paris, actually, in June 18 to 22nd, 2018. If you have any interest or if you know somebody who would like to follow this class, I really invite you to contact Claude Renaud. You have his email address here. It's claude.renaud@cea.fr, or you can send me an email. I'd be happy to forward that to Claude and his team. So again, thank you so much, Professor Dong, and I leave the floor to Bertha for the Q&A part. Thank you.
Thank you, Patricia.
Okay. Any question or comments?
So there are several questions typed in. The first one that I see is a comment, really. Welcoming and congratulations from a colleague in Germany. James Martin has a question on why did you go straight to 2 reactors for 1 steam turbine, and the market may prefer 100 megawatt plants. Do you see that? Do you see that question?
No.
In the Q&A pod?
No. I can see the comments from Johan Michaels. Welcome.
Okay.
Congrats.
Change the view to the presenter view. Along the Q&A, you'll have 2 tabs, the one on the left with a person in front of a computer screen. If you click that, that will allow you to see the questions as they come in.
So firstly, I can answer that question. Why did we select 2 reactor module plus 1 steam turbine? Because in our country, in China, we need an economic nuclear power plant. According to our analysis, 1 modular reactor plus 1 steam turbine generator unit, its economics is not good. So we think the roadmap should be multiple module plant, such as we are designing the HTR-PM 600 6 reactor module plus 1 steam generator unit. we can improve the economics of the nuclear power plant. So at the demonstration power plant, we selected 2 reactor modules and 1 steam turbine.
Thank you. The next question refers you back to slide 9, and it talks about the megawatts efficiency. The megawatt is 211, and the megawatt thermal is 250 for 84% efficiency. And how were you able to achieve such a high efficiency?
Pardon? Could you repeat that question?
On slide 9?
See that. Yeah.
Do you see it? On slide 9, the megawatt.
Slide 9. Yeah.
Okay.
Yes. On slide 9, the efficiency of the power plant is about 42%. Oh, I'm sorry.
Nope.
Yes, I can see the question on the Q&A area. As I explained, there are 2 reactor modules in the demonstration power plant. So the total thermal power is 500 megawatt, and the electrical power is 211. So the efficiency is about 42%, not 84%.
Thank you. The next question is, what is the electrical consumption of the HTGR to generate the 211 megawatt electrical output?
For the plant consumption, it's about 7% of the total output. So totally about 14 megawatt.
Thank you. How is the buildup of noble gases in the helium fluid, especially those that are neutron absorbers, controlled during operation?
In this plant, we have helium purification system. It will operate every day and keep the quality of helium. But I cannot give much more details. We can keep the quality of helium with the helium purification system.
Yeah. The question from Kristen Burke came in. I noted during the presentation that you may have addressed this near the end, but the question was to share more information about the consultancy which checked the feasibility study. There you go.
Yeah, I got it. In China, there is one big company. The large engineering project will be reviewed by this company, and including some large international engineering projects. So our HTR-PM project was also reviewed by this consultants company. China International Consultants Company. China International Engineering Consultants Company.
Thank you. Can the fuel pellets be recycled to produce other true fuels? How is that accomplished?
Can the fuel pellets be recycled to produce other TRU fuels?
Correct. Transuranium.
Transuranium. Sorry, I'm not familiar with this area.
I can say a few words about and Professor Dong, if you want, about recycling the triisofuel. Most of the time, it's preferable not to recycle this type of fuel because it's extremely difficult to recycle them. They have been engineered in a way that you just do not want to recycle. We did at INL a few experiments trying to recycle this type of fuel with the microwave, trying to break down the fuel. It's very difficult. So the goal of this type of fuel is to be used, but not to be recycled, as opposed to other type of pellets, which is much easier to break down.
Thank you.
Thank you.
You're welcome.
There's a question on what is the estimated cost of generating electricity?
Cost of generating for our demonstration power plant, the specific capital investment, the capital cost is about 40,000 renminbi RMB per kilowatt. So I'm not sure the exact cost of electricity, because this demonstration power plant is delayed, including the delayed starting construction, and also the construction period is delayed. So the cost of generating electricity will be higher than normal nuclear power plant. But for the following up project, I think we can reduce much cost compared with the demonstration power plant. For the demonstration power plant, maybe 60 cents in renminbi, RMB.
Dr. Kelly's question is, what is the design burn-up for the fuel?
Gigawatt per ton. 10 gigawatt a day per ton.
Have some accolades. Thank you. There's a question on why are control rods needed. There's no need for emergency shutdown, so the normal closing down for maintenance, if any, could be achieved with the stopping fuel influx.
That is a very good question. As you know, this is the first high-temperature gas-cooled commercial-sized reactor, the nuclear power plant in China. So we have no complete regulation document or special rule for high-temperature gas-cooled reactor in China. We designed this demonstration power plant based on the rules for PWR. For PWR, normally there are two different reactivity control systems. So as the first step, we also designed two type of reactivity control systems. But in future, we hope we can simplify the reactivity control system. Thank you, Johan.
would happen in accidental condition if a hot pebble would enter in the direct contact with air? Is graphite fire a risk?
No, no graphite fire. Actually, we did some tests outside the reactor. We lighted the gasoline and on the graphite pebbles, but no, there was no graphite fire.
Thank you. Is there any R&D you would like to suggest to reduce the cost for an nth of a kind plants? I'm not sure for a nth of a kind plants.
As I said, the current steam generator is a complicated component. We are also thinking about the design and the manufacturing, including the material and so on. But that's very difficult to determine such an issue because we have spent a lot of money for demonstrated such design. If we change the design, we must redemonstrate the prototypical components. So in our following up project HTR-PM 600, we try to keep the same safety feature, the same components, no change.
Thank you. Several people are expressing their appreciation and thanks to your presentation. Does the 600 megawatt electrical plant include reheat?
No. We don't change the components. We just connecting 6 modules to one steam generator, to one steam turbine. For each reactor module, it is a complete duplication of the reactor module in demonstration power plant. So there is no reheating.
We still have several questions. Are you good for time to continue answering?
Yes.
Okay. The next question is, how far are we from HTR operating with an outlet core temperature of 1,000 degrees C? What is the gap of materials, for example? Can the current composition of pebble of the HTR-PM be used as such? And what are the limitations, if any?
Of course, I think one challenge is the fuel element. We have made the irradiation test and PIE, the heating test according to our design. So if we try to raise the outlet temperature, we must repeat such a irradiation test. That's the fuel pebble element. Another challenge is the metal materials. In our design of a steam generator, the high temperature metal is 800 H. So if we increase the outlet temperature, we must find a new material.
Thank you. We may have addressed this one already. Is it difficult to do reprocessing of spent fuels?
Yeah, I can take this one, Bertha. It all depends on the spent fuel that you're talking about. If you are talking about a spent fuel that is coming from a light water reactor, it's easy. You have examples in France, UK, Japan. They're using the Purex process. But if you are talking about the presentation today on the triso fuel, and I refer you, I think it's slide 17, where you can see the triso particle. You see the different layers of the, for example, you have the carbide. This is very difficult to break down, as I explained earlier. You can do it, but you have to think in your mind between a benchtop operation and then going to an engineering scale, and the cost, and does it make sense. So in my opinion, and I'm not talking for DOE, I'm just talking for myself as a recycling expert, I will tell you it's better not to recycle triso fuel. They have not been made to be recycled. Thank you, Bertha.
Thank you, Patricia.
Thank you.
What equipment is used to balance the pressure of steam coming into the steam generator from two reactor vessels?
Of course, we have valve, and we have also the measurements related to fresh steam pipe. So we can adjust the pressure through the valve movement. And also at the end of feed water, we can also adjust the feed water pump.
How many pebbles are discharged from the core per day, and what are the limits of the fuel handling system?
Normally, every day, 400 fresh fuel element will be charged, and also 400 spent fuel element will be discharged. And the number of fuel element circulating every day is about 6,000 per day. 6,000.
Thank you. Did you perform a probabilistic risk assessment? The OPEX in this area is not very large.
Yes, we did. The OPEX in this area is not very large. What is OPEX?
I'm not familiar with that acronym. Patricia, are you?
No, I'm not.
So, Lotte, if you want to clarify in the box, perhaps, we'll go to the next one. Could you explain more details about the economic, maybe the key factors?
That's a complicated question because this is the first HTR-PM power plant in China, also the first one in the world. We ordered the component, but the manufacturer, they manufactured the component as a first of a kind component. So that's so the cost of each first of a kind component will be higher than normal price. That is one aspect. Another aspect is the construction period. Originally, we planned a construction period 59 months, but currently the construction period will be prolonged.
There was some clarification that came in to define OPEX as the operation expenditure. And perhaps as a follow-up on that, a question is whether or not the economics include decommissioning of the system.
Yes, we calculated the cost, also including the decommissioning cost.
There's some follow-up to the more of a comment, really. Actually, the fuel can be recycled using electrohydraulic fragmentation, both for waste volume reduction and for symbiotic fuel cycles. If this is desirable, the process works, but still needs to be upscaled industrially. Could you share some information on possible ideas for safeguarding the fuel particles?
So maybe I can't answer this question at once. Maybe I can answer the question by email.
Yes.
Simon Cardinal, yeah.
Yeah, we will send you the email, Professor Dong, of some of the questions, because when I see the list of questions, I believe there's a strong interest with your presentation. So it's already 10 a.m. in the United States on the East Coast. So I want the people to understand that Professor Dong is in China, and it's already 11 p.m. 23 in China. So you know, he has a long day. I'm sure he starts like everybody else around 8 in the morning, so it's a very long day for him. So I would propose that the next questions could be sent to Professor Dong, and I'm sure he would be happy to answer to the questions. What do you think, Professor Dong?
Okay, that's a good idea. Thank you.
Yes, I take the opportunity to thank you again for volunteering to give this webinar. I saw a strong interest, and I thank the audience for their participation. And I'm thinking maybe sometimes to put all the questions in a written form and the answers for all the webinars we have been doing since September 2016. So thank you again, Professor Dong. Thank you also, Professor St. John, who was behind the scene. Thank you, Bertha and Amanda, for all the logistics. And I invite you to join us again on the 21st of February with the presentation of Dr. Stu Malloy. So thank you, everybody.
Thank you. Bye-bye.
Bye.